was kind of funny. That Greg was like, well, at some point Mike's going to be talking about, this qualitative versus quantitative. Ta-da!
Isn't it fluffy?
So what we're doing, because last week, or not last week, Tuesday, we kind of talked about Chapter 1. So if you've gone through and done the reading, Chapter 1, I would argue, to use Greg's term, is kind of fluffy. Okay? They make science look like this, it's just this really simple puzzle thing. And it is kind of this really simple puzzle thing. It's all about those observations and how we put them together and organize that thought. Okay? We then jump from Chapter 1. We skip past, if you're looking at our 7th edition textbook, we skip back 2-ish chapters, PSS, which that's one of the updates they made in the 7th edition so that they could sell a 7th edition. They changed the chapter name, okay, but officially it's a chapter. And then Chapter 2. We're skipping both of those because those are all dealing with mathematics, and we aren't going to deal with that quite yet. So really our first unit is talking about the basics behind what we think about chemistry. In Unit 2 and Unit 3, that's when we'll come back to those mathematics. Okay? So we'll jump up into Chapter 3 and look at our big classifications. And one of the big classifications is thinking about matter, okay, and where it came from, okay, or how we would classify it. And that's where we encounter these two types of observations, qualitative and quantitative. Okay? So what do we have in the picture? Okay. Way to be specific and catch the little pun there. Okay. We have a sheep, also known as potentially a ewe. I honestly don't know because I didn't check. So we have some kind of sheep, okay, within this. What else do we have in this?
Bushes.
What's that?
Bushes.
Bushes. Okay, are these qualitative or quantitative so far?
You have two.
Okay. So if we go through and specify that we have 2 sheep, what have we done? Quantitative. We've applied a quantitation, okay, a numerical value. We have 2 sheep. If all we're really doing is bringing in sheep, it doesn't really fit under either of those. Okay? So what other observations could we do beyond sheep? Okay, and I heard bushes. And I would kind of drop those in qualitative, but I would argue we could do a little bit better to make it super clear that it's qualitative or quantitative. The root of quant was, sorry, as I give you the root of quantitative was quant, which is an amount. Okay, so a numerical value. So we've got a numerical value of sheep, so we could do that. Okay, the root of qualitative. Qual, like, quality. Okay, so what could we possibly be referencing for the quality within this image?
A good-looking sheep.
Okay, we could reference it as a good-looking sheep.
High definition.
Okay, good-looking. Okay, what might you use the sheep for?
To shear it.
To shear it, so we could actually reference the quality of the wool. Okay, what else could we use the sheep for? Meat. So we could reference potentially the quality of the meat. That's a little bit more difficult to do, but we could do that. We could say it's high quality meat. Okay, what are our grades? Choice? What's better than choice? Prime. Let's go with prime meat. Okay, that's qualitative.
Prime meat, not prime meat considered.
Nice try. How else could we spin? Because that's looking at the wool, the quality of the wool and the quality of the meat. Could we still make an observation about the wool and the meat that is quantitative? Okay. Give me an amount.
10
Say that?
10 pounds of meat.
10 pounds of meat. Okay. The quantity of the wool?
We're not eating lamb here.
We could be.
Black sheep? They aren't black, but yeah, okay. So only one person got it, that's fine. Okay.
Oh, I got it. I just want to say.
So we could look at different ways to represent these. Okay? Which one's more important?
They're both important
Why?
for a reason that probably will be explained by you.
Okay, we could use that. Why would those values change, or our importance of one of those observations over the other change?
Sometimes you want to have
What are you looking for? So
quality over quantity, maybe,
why?
because you'd rather have something that's like of a better like standard than to have like a lot of it, right?
Okay, so, and I like that, but let's try and zero in and get more specific. And we could even use phraseology, let's just accept that, from the boards around us.
Well, I remember one of my teachers back in the day when he was explaining writing, he said that I could go to this restaurant, get like a big plate for really cheap, or I can go to this really fancy restaurant, get a steak about this big, and it's the best thing I've ever had.
Okay, so let's use that restaurant as our kind of qualifier. Who's producing that meal?
You want to, I would make sure
The-
the health of the animal, if it's being taken care of.
Okay, so that could get back up to this quality. That could tie to potentially why it's prime meat and not choice or, there's another one, right? There's animal grade, I guess. Okay. Who's preparing that meal? And there was a statement for animals, and again, this goes back to I appreciate you sharing, but if I walked into the kitchen, am I going to see a sheep cutting itself apart so that it can cook itself for me? Probably not. Who are we going to see? The chef. Okay. Where is the chef? How is the chef deciding that one piece of meat, I just want a whole bunch of stuff out there, or I want high quality?
Training.
Okay. Their training and experience, or potentially their decision about what they want their restaurant to do. Okay. So this information is the same for both of those chefs. They're now going to weight those observations differently. The one chef that just wants the quantity probably just cares about the amount of meat. That one chef that said, I got a really tiny, or when we go to that one restaurant that had a very tiny amount, but it was the most flavorful, fantastic thing they ever ate, the chef probably didn't care about the quantity. They probably cared more about the quality. So what changed in both of those cases? We have the same observations, but the interpretation of those observations changed based on what?
Personal desire preferences.
Let's see, where's this stupid word? Yeah.
Perception?
Perceptions could kind of work. We could kind of look at a purpose. Our audience. If our audience changes, we're going to change which observations become important and how we want to emphasize those, which gets kind of towards our rhetorical aspect. What is the purpose behind making those observations? What are we trying to get out of it? And depending on what we want, we may bounce back and forth between those two observations. Okay, so the statement, which was very leading, so good job on catching that they're probably both important, but it depends on the circumstance. It really is depending on the audience. How are we trying to pitch that? So when we go through and do science, we have to be making observations in both cases. Because in one case, we may decide that the qualitative observation is more important than the quantitative. Okay? Why do most people struggle in science? Well, when we go into science classes, typically what do we look at? We typically look at the quantitative. And because we're looking at the quantitative, typically what do we end up doing with all of those numbers? Math. Okay? There's a reason why math is one of the kind of most difficult courses people struggle with. Okay? Science is taking the math that everybody didn't like and providing a context behind it So we're layering information on top of a subject that people already have troubles with. Okay? Why do we spend most of our focus looking at the quantitative? Because most people have a hard time with that. Okay? The issue is that we then lose some of that qualitative observation that becomes very important. So when we move through, realize that you're looking at both. We'll unfortunately spend a lot more time in the quantitative, but the qualitative can really help us out. Kind of make sense? Okay. We're going to take kind of a quick moment here because I was not surprised by a visitor last Tuesday and instead got surprised by a visitor today. So, remember our context of getting help on Tuesday? Okay. How could you get help? Tutoring center. Let's start with qualitative observations. We've all existed for some number of years. We might have been able to make an approximative quantitative observation on light. What is 70–80% of life? No, what is the composition? So what is the thing that makes up 70–80% of life? Water. Okay. There are cells, and yes, those contribute to life. Do you have more, or did you forget something? Forgot something. Okay. So water is contributing to it. And water has a very important central aspect of life or of science, largely because it makes up such a large percentage of it. Okay. But one of the extra benefits of water, more so than any other kind of substance, has to do with roughly the images shown here. What are we seeing? And I know they aren't perfect pictures, but they aren't horrible.
Different forms of water.
Right? We have the different forms of water. We've got snow, meaning we've got solids. Okay? And I should have picked a better picture, but this was a prettier picture. We also have liquids, and we have gases. Right? And what makes water so kind of key is that we can have observations about all three of these phases. We can see, or sort of see, these three phases in other systems, but water is the one that allows us to see that these three phases are interconnected. Okay? That we can convert from one phase to another without changing the substance, and we can reverse backwards. Okay? So that makes water kind of neat in that respect. So what could we observe about solids that make them unique from liquids or gases?
You can hold them.
What's that?
You can hold it.
Okay, we could potentially hold them. You can't hold a liquid? What do you mean an extent?
Like it'll be on your body, but if you don't feel like you're holding it, like grasping it.
You shape a solid.
Okay, so the solid does what with its shape?
It holds a form.
It holds its form. Okay? So we can really hold them because the shape doesn't change. Doesn't change is a lot of letters. And immutable is hard to spell. Static. I'm going to go with that one.
Delta with an X over personally.
Yeah, I'm going to write static. Okay. What would liquids? I can cup my hand and hold a liquid within it, but as soon as I open my hand up, what's going to happen to the liquid? It's going to run out. Why? What happens with a liquid's shape? Changes. So the shape changes. What about a gas? Would I be able to hold a gas? No. So does the shape for a gas remain static, unchanging, or does it change? It changes, but now gases have an extra kind of thing associated with it. Okay? Not only does it change, I can't even really hold it. Because what are gases doing? They're flowing. And ultimately, what are they, if we continue to push that, if I tried to hold the gas, where's the gas that I'm trying to hold going? It's dispersing through what?
Air.
Air is gas, so I don't quite accept that one. If I had a balloon and filled it with gas,
Whatever's holding it, it's like a water bottle.
whatever's holding it, okay, its shape changes because its volume will also change. Okay? The shape of air is roughly approximative to the container that holds it. Okay? What about liquids? Does the volume of the liquid change? So the shape changes. Does its volume change? No. Okay? It can change roughly where the volume is, but the volume is static. Okay? What about the solid?
It doesn't always have to be static, does it?
If it's going to be, which is going to bring in a whole nother can of worms that we don't quite want to approach, we're going to run with the assumption that it does hold static. Okay? I don't know why I'm writing hold. I do know why I'm writing hold, but that's not what I wanted. Okay? Which is going to bring in the next kind of big change here. So solids, everything about them is effectively static. Liquids, your volume is static, but your shape can change. Gases, everything's changing. Okay, so there's a last big aspect that can kind of go with these that your textbook presents. Begins with a C. Okay. Different conjugation of it, but that works. We could look at compression. What are we talking about when we think about compression? What's changing? Okay. Density's changing, yes, but the problem with density is density measures two different things. So let's simplify it. Okay, as a hint, it's already up on the screen. The volume is changing. Okay, so when we're looking at compression, if we take a look at a solid, would I expect much compressibility, which is the word I was fishing for, but compression works? Would I expect much compression? Why not? Okay, the shape and the volumes are static. Okay, they're locked into place. Okay, so I get no compression. How about a liquid? Can we compress a liquid much? No. Not really. There's a little bit, but there's not a lot of compression either. To our first approximation, because we're looking at our qualitative observations, we're looking at no compression. How about a gas? Yes, we can compress a gas. Okay, so we do have some compressibility. Whoa! We do have, we'll call it significant compression. Okay, so now that I've written all that, I'm going to erase it all, because what we want to do is now come up with a model to represent what we just described. Okay, so now I'm going to pick a small piece of solid. Okay, and here it is. This is my representation. If I have a solid, am I going to have a single particle, for lack of a description? All solids are a single particle. No, they're made up of multiple particles, right? So where would I put the next solid particle? Right next to it. And right next to it, right next to it, right? So this would be what our solid would look like, right? What would our liquid look like? Okay, a little separate. Why would we want them to have a little separation there? They're fluid. There's a little bit more motion associated with it. With the solid, we don't have any motion. Why is there no motion? There's no space to move. Okay? So when we move to a liquid, we might have a little bit more space in between. Okay? But for the most part, they're pretty close. Gas? Really far apart. Okay? Those rough approximations, okay, can allow us to make conclusions about how we would expect each of those phases to interact. Okay? So when we move further into the semester, we'll come back to these topics and be like, well, how could we quantify those aspects? Okay? But all we're trying to do is establish simple things first. Make sense? Cool. So matter is made up of these three phases. What could I do with those three phases? Okay, so we get a bunch of ways that we could branch out matter. So we'll look at it as pure substances and as mixtures. So if I took a solid and a liquid and I put them near each other, okay, it might look like a mixture. And depending on what those substances were, we'd have to worry about kind of our referencing. Your pure substance is saying that we have the same chemical linkage between every particle within that phase. So if I mix a solid with a liquid, okay, say solid ice with liquid water, they're both made up of the same substance. So the phases may count as a mixture, but everything in it is pure. Okay, so we get into a weird kind of system when we start mixing phases. Make sense? Okay. Mixtures are spatially linked. Okay, they're not fully integrated into each other. Okay, so if we looked at, well, and that's where it becomes challenging. Let's focus on our mixtures. We're looking at spatially linked, not chemically linked, and those mixtures can then split into two categories: heterogeneous and homogeneous. Okay, a heterogeneous mixture, we're looking at our roots, hetero, okay, we see at least two different things. Okay? Hetero relationships, male, female. Homogeneous relationships, male, male, female, female. Okay? Different, same. Okay? In a heterogeneous one, we have multiple visible phases. Okay? Notice visible is in quotes. Why in quotes?
It's not always visible.
The human eye isn't perfect, and we will potentially encounter cases that are gray area. They're hard to distinguish. Okay? And in fact, we will talk about those cases. Homogeneous. There's no visible separation. They're all evenly mixed. Okay? Any guesses for a mixture? And don't pick ice and water. Not allowed to do that one. We want two different substances.
For the heterogeneous,
Either. Doesn't matter.
water and oil.
Water and oil. What do we have for water and oil? Heterogeneous or homogeneous?
Heterogeneous.
Heterogeneous. Because when I mix those, what happens? They separate out. So if we look at oil, come on, pen. Oil and water, there's a visible separation there. Right? And what I would argue is a kind of a more simple explanation of that is don't try and think about the chemical linkage, but think about the phases. If I see different phases, it is best to reference that as a heterogeneous mixture. Okay? What is the phase for oil? Solid, liquid, gas? Liquid. What is the phase for water? Damn it, didn't I just say two different phases? Do those phases mix? No. So it's not just that they're different phases, solid and liquid, or liquid and gas, that's the other one. Okay? It's that those phases don't interact with each other. Okay? So we're looking at two or more phases. What else could be potentially a more explicit heterogeneous mixture? Has anybody tried to go for it?
It would be like a rock and water.
Perfect example. I was going to go with a really, really, really small rock known as sand. Okay? But that works. Okay? We try to dissolve a rock into water or sand into water. That is now a mixture because they are spatially near each other. But is that mixture heterogeneous or homogeneous? It's heterogeneous because we can see those two phases. Okay? What happens if I take oil and water or even sand and water and I shake them up very, very vigorously? The instant I stop shaking, what would you see? Just the instant. And so we could look at calculus, instant versus time, all sorts of nasty stuff like that. So don't think about, well, right after I stop shaking it, I slowly start to see them separate. You're saying a time, and there's no time. Instant. Shake, 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 poof. It's together. Which would suggest?
No separation.
No separation. It would start to suggest homogeneous. That's why it can become tricky to evaluate those. Okay? So we aren't looking at a physical excitation of these things. We're giving them the opportunity to establish themselves on their own. Once we've given them that opportunity, we evaluate. So we aren't shaking, 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 oh, instantly they're all mixed, so it must be homogeneous. Give it time to be like, okay, this is what I want to do. Okay? So don't include a physical agitation to make it homogeneous.
So going off of that, you wouldn't consider like if you put a Kool-Aid packet in water, that wouldn't be homogeneous, right? Because you have to shake it for it to become that one thing.
Okay? So the Kool-Aid mixture is actually one of my favorite examples. Okay? Largely because I was tortured as a kid. Everybody wants, and mildly tortured. Okay? Everybody likes Kool-Aid, right? Everybody knows what Kool-Aid is. Yeah, like a nice little sweet drink that comes in a little sugar packet with flavoring and you pour it into the water. We were definitely allowed to have Kool-Aid growing up, or Tang, if you prefer Tang. Okay? Oh, I was laughing at Tang. Tang's pretty awesome. Okay? Vitamin C all the way. Okay? So we were allowed to have that. But my parents didn't like how much sugar we'd be ingesting with it. So in the process of being allowed to have these beverages, we were not allowed to mix them. Okay? So to make Kool-Aid, we're like, can I have some Kool-Aid? Yes, you can. You can add the Kool-Aid to the water. You're not allowed to mix it. What happens with time?
It ends up
It dissolves.
It does eventually form the homogeneous mixture. Okay? It takes time for the solid to transition into that homogeneous system. Okay? So there are cases where we will have to mix it to speed up that time process. Okay? Just the same with the inverse, with oil and vinegar. Okay? I can shake up oil and vinegar very, very vigorously so they're mixed, and then I quickly pour it on my salad dressing so that I get a mixture of both of them. But what happens if I just shake it up and leave it alone? It separates back out. Okay? So in both cases, I have to give it enough time to make that observation. Okay? So the Kool-Aid example, you might say, well, I see two phases. Give it the time, what happens? It turns into the homogeneous system. Okay? So when we're making these assumptions, time isn't a factor. That's a difficult thing for us to process because time is always a factor. That's why we have cell phones, and the very first thing you see when you turn on your cell phone, freaking clock with the time on it. Okay? That's why every room has a clock in it. This is why casinos don't have clocks in it. Okay? Because we don't want people to have a perception of time, so they continue spending money. Okay? So time becomes something that we've ingrained into our culture and into our brain. When we try to make these observations, we're trying to ignore the effects of time. Okay? So we mix them, let them figure out what they're going to do, and then make our observation. Okay? Was it copyrighted? Trademarked? I don't know. Okay? So Kool-Aids are a good example for our homogeneous. What would our phase comparison be? How many phases would we expect for a homogeneous mixture? One phase. And one phase only. Okay? Just to throw a big old monkey wrench into this right out of the gate, what is the phase of Kool-Aid? Okay? So, touche-ish. How many of you drink solid Kool-Aid? Okay, interesting. So I don't accept your answer for solid. Okay? When we buy the little packet, sure, it's solid, but when we drink it, it's liquid. Liquid, those phases, solid, liquid, and gas, are referring to pure substances. Are we a pure substance when we're looking at Kool-Aid? Nope. We're a mixture.
So does that mean that the powder would be a liquid then, or?
Well, the powder comes in as a solid state. The liquid, which in this case is water, comes in as a liquid state. What happens when we mix those two things? Well, it's now not a solid and not a liquid because those reference pure substances. So what is this new phase? Well, it's a mixture of things that came out to a single new phase. A single new phase called The Kool-Aid phase, I like it. Aqueous. Aquafina is water. Okay, aqua. Aqueous is water. Dissolved in water. So we end up seeing a fourth phase come out of it. Why do we invent this new phase? Because we need a new way to describe our mixtures. Okay? Could I dissolve something in something other than water? There's too many somethings, but you get the point. Yes. Could I call those aqueous?
No.
No. So what would I need to do?
Create another phase.
And create another phase. Okay? There's bunches of different liquids that we could potentially dissolve things in, which would mean we have billions of phases. We don't invent new phases. Why do we only invent aqueous?
You got lazy at one point?
Yes, it dissolves in water. Why is that important to identify as aqueous?
It's using water.
It's using water. I agree. Why is it important to identify it for water, but not for anything else?
What are 70 to 80% of life?
70 to 80% of what we do and work with is water. That's why we're inventing a new phase for it. Okay? All the other ones get called solutions. And water is officially a solution, or the aqueous phase is officially a solution, but because it's dissolved in water, and water is such a common solution, we reference it as now aqueous. Make sense? Okay. So you think you guys got a difference between hetero and homo? Almost, okay.
If the substance doesn't dissolve, though, it's not aqueous, right?
If it doesn't dissolve, it's not aqueous. Okay, because if it doesn't dissolve, has it mixed evenly with the water? No. You don't have a homogeneous system. You'd be heterogeneous. It's not aqueous.
I'm still a little iffy with people phases. So when you say phases, it's more like it starts out as this, then goes to that, right?
Yep.
Okay. That's why I was a little confused with the homogeneous, because with the Kool-Aid example, it's still involved with a solid going into a liquid. But you just say it was a liquid.
So remember, it's the state that we're referencing.
Okay.
Okay. So if we look at the Kool-Aid example again, okay, there's really three different states we're addressing. One state is
Water.
water, which is a liquid. Okay. Have I mixed anything yet? Nope. So I'm not even in the mixture system. I'm in the pure substance, which we'll shift to in a second. Okay. What's the other state? The Kool-Aid powder, okay, which in and of itself is a lot more complex because, yeah, but let's just say Kool-Aid was a pure substance, but let's just say it was, okay? That's now in the pure substance category as a solid. Okay? What's the third state? The mixture of the Kool-Aid and the water. Now that I've created a mixture, I now have to decide, is that mixture heterogeneous or homogeneous? This is where that time factor comes into play. We can't look at it at the initial state of the little kid staring at the pitcher of water with the Kool-Aid sitting at the bottom and slowly mixing in. We have to wait for the little kid actually drinking it.
Oh, okay.
Okay? So we have to ignore that initial time state to set us up for this classification. Okay? And in that classification, when we look at the final form of Kool-Aid, it is a single phase. That single phase is aqueous. Kind of got it?
There's a poem from the 1800s that says the house that is a building is not that which is built. So you have to wait till, in essence, the solution's fully built before you can really engage it.
Is salt water considered aqueous?
Okay. If I take salt, what phase? Solid. And I take water, liquid, and I mix them.
Yeah.
What happens?
Salt.
The salt dissolves, and I end up with what we would call salt water. That new, it's weird to call it a new substance, but let's call it a new substance, is what? It is an aqueous solution. It is a mixture of two chemically different substances, salt and water. How do we know they're chemically different? What stands out at them that helps you to decide that they're chemically different? Their initial forms. When I look at salt, it's a solid. When I look at water at that same temperature, it's a liquid. That can help me determine that they are indeed different substances. I then mix them, they dissolve, there's that initial time delay that we have to worry about, but that time delay then sets us up with the new state. That new state is a homogeneous mixture because I only see one phase. Because I now have a phase is, well, what is that phase? It can't be solid, liquid, or gas because those officially apply to pure substances. This is no longer pure because I have two chemically distinct things. Okay? That's why we invent aqueous. Okay. So I got your question. Gabe, it looked like you guys all had the same question? Okay, cool. So let's be extra obnoxious with my favorite example on this. What is fog? Hats off, good gesture. It is opaque. Okay, we could reference it potentially as a gas. Okay, what is in this room right now? Air, which is a gas. Okay. Can you see through this gas? That's why you can see me. Okay. That would be an interesting lecture room. Okay. An interesting way to exist, too. Okay. Can you see through the fog?
Sometimes.
Gabe, I'm pointing at you for a reason. Sort of pointing at you with the iPad.
Yeah.
What did you say fog was?
Opaque.
Opaque, which is a fancy word for saying?
Clear-ish. It's like...
That's what opaque means? Dang, do I have the definition wrong?
I don't know the definition. I'm not really a man like you.
Okay, good. No, I was like, it took me forever to try and figure out that definition. You can't see through it. But if it's all gas, then I should be able to see through it. Why can't I see through fog? It's mixed with another phase. That other phase is causing light to hit and bounce or reflect. That's what makes fog difficult to see through. And it depends on the concentration of fog. Don't open that one either. Okay? So what is happening with fog? It appears to be homogeneous because we can't really say, well, that's a gas particle and that is the fog particle. It's all evenly mixed. The only reason we know that they're two different things is because of how light interacts with it. So our visual cue on it becomes very challenging to place it. It's only after we start to really process the distinction between these and what those different phases would do to each other that we can establish that fog is actually a mixture of phases. One of those phases being the gas that we all breathe, because otherwise we would die when we walked into fog, right? And really, 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 really tiny water, liquid water. So that when the light hits, it refracts, and that's why light doesn't pass cleanly through. And that's why it has that opaque, word of our day, okay, characteristics to it. Which would mean fog gets classified best as heterogeneous because there's two phases. Okay? So we end up with fog, which is this really weird, like, well, it looks homogeneous, but because of my secondary observations, it's heterogeneous. And that's a challenging one to identify. And the biggest issue here is that when we talk about and think about heterogeneous versus homogeneous, we see them as how many boxes? As a hint, it's literally drawn like that on the board. 2 boxes. It's not 2 boxes. It's a continuum. At one end, we have heterogeneous. At the other end, we have homogeneous. Depending on where we are in that continuum, we may decide it's one or the other. Most systems that we deal with allow us to very clearly identify which one's which. Not all. Make sense? Okay. Greg's got something to say.
So as we went through that analytical process to come to the conclusion, I just want to pull apart some of those things. So first we described made our observations, right? Scientific processes, writers are scientists, scientists are writers. So we described the fog as both gas and water, right? And then we took the we had to pull apart those constituent pieces. So that's analysis. So we used description and analysis in that step. Then we had to synthesize it back together with the definitions of a mixture and the different types of mixtures, and evaluate what that lined up as, and then make some sort of claim, value judgment about which category that fit into. Are you following that process? To get to that last step takes more work than just to say fog is tiny liquid and gas, right? It's easy to say fog is tiny liquid and gas. To get to, because of that and our definitions of mixture, it is also a heterogeneous two-phase mixture. Like, that takes more cognitive effort. That's all I have to say about that.
It's stuff like that. It was like, really? It's pretty cool on how we can break down the English language and apply that back to what we're trying to represent within science. Okay?
What would, like, I don't know how it's to do with that, Jello,
So if we're looking at Jello, I don't think I know enough chemical composition on Jello, but I would probably place Jello as a homogeneous mixture, because what you've done is taken water and gelatin to form a homogeneous solution, and then what happens is the particles within Jello or the gelatin connect to form a lattice that holds it all together as one phase. The real fun thing with that is Jello a solid? You're going to be kind of inventing a new phase to describe that. But I would argue that that's going to be a homogeneous mixture.
Okay, so it could either be a mixture of pure substance, it can't be one or the other, like both.
True.
So fog is a compound. It's not.
Fog is a mixture. We're not on pure substance. So fog,
Oh, it's a mixture. Okay.
yeah. So fog was a mixture of two things. What were those two things? Water and air. Ultimately, it's a step beyond just water and air, because what is in air? Oxygen and, sorry, carbon dioxide. Okay? So air on its own is a homogeneous mixture. Okay? Air on its own has water in it. Only when the conditions are right does the water actually come out to form liquid water, rain, or fog.
It's one of these. This is a common thing people get mixed up here, is because mixtures and compounds outside of chemistry are used synonymously by some people who aren't specialists talking about chemistry. So if you've got a compound or you've got a mixture, they may say mix the compound. So if you are having a hard time just making that distinction, the more specialized you get into a particular area, the more you have to discern between language that sounds really similar. In this case, mixture and compound in a generic sense might be used interchangeably, but within the chemistry context and environment and sociocultural structure, they are very distinct things.
Yeah, I think in that reference, like pharmacy, like you can compound a drug, which
Yes, I remember that.
Yeah.
I think is really just a mixture.
Yeah.
I don't think that's actually a compound when you compound the drug. It's a mixture of,
I get a compound.
and I don't know enough about pharmacy to answer that, but I vaguely have heard those terms. Yeah, what do you got, Haley?
Just debating.
And you're looking at the periodic table, which is already making me go, non-mixture, pure substance.
Yeah, no, that's what I was gonna go. I thought
Okay.
we were starting to talk about that.
Yep, that's what we're going into, so
Okay, so
start us off.
A compound would be, well, an element would just be one single thing. A compound would be whenever you mix two of those, so salt would be a compound because you're mixing the, I'm really bad, Na and Cl.
Good. Yeah. So a couple things that I would go off of that. You said mixing elements. That's already going to be
They're not-
language-based
Okay,
a little bit weird. And that's fine, because you don't have the words yet, the definitions, to be able to apply that. I would argue we're reacting sodium with chlorine to make sodium chloride, okay, a compound. So within our pure substances, these are now chemically linked. And that becomes really hard to address, because the name of this course is chemistry. How many of you have taken a chemistry course before? Half the class. The official prerequisite for this course is how much chemistry? 0. The second day of class, we are defining a term using a term that you're supposed to learn by the end of the semester. Logically has some issues behind it, okay? So we encounter things like that every so often, and that's because we haven't come up with the language to represent that better. So what we're talking about when we think about this chemically linked becomes a bit challenging, right? So chemically linked doesn't really help us with the pure substance until we moved into what these are. These split into 2 categories, elements and compounds, okay? An element is only one type, okay? So if we look at our periodic table of elements, as long as I look at a single box, I can have multiple of that same element floating around. Those are all considered chemically linked, okay? Because it is one element. The instant I now combine that element with, say, something else, okay, and chemically link it, it's now a compound. Okay? We've already talked about a compound this semester. What compound did we talk about? In fact, even today. H2O. Which was? Water. If you don't know that formula, that's okay. That's partly part of the class. So we get the formula H2O. What elements make up water? Hydrogen and oxygen. Okay? Which is also kind of neat because you already knew that. You already knew some chemistry. Okay? And you knew that because either you knew what those symbols meant and tied them back to what you knew they were, or you just memorized that water is hydrogen and oxygen. Right? So when I combine hydrogen and oxygen according to this formula, I now have water. What information is embedded in this formula? We have hydrogen and oxygen. We're using the first letter of each of those to simplify it, and how do you know there's 2 hydrogens?
There's a 2 in it.
There's a 2. Why does it mean 2 oxygens?
Because it's behind the H.
The location of where we place those numbers holds meaning. Okay? Some of you already had that. That number placement after and lower than the symbol is referencing the amount of the symbol in front of it. Kind of make sense? Okay. Does hydrogen exist on its own, outside of water? Yes. What did I say? Hydrogen, didn't I? I'm not breathing in hydrogen. I meant oxygen. Okay? So if we looked at oxygen that we're breathing in, we would have the element by itself. It turns out oxygen is special, and it has to be with another one. So when we look at oxygen, there's 2 elements that go with it. Okay? H2O we would classify as a compound because they are chemically linked. Okay? Chemically linked and compound. Okay? Oxygen was special. It gets written like this. Do you see any other elements around it? No, which means this is now an element. Okay? Because it is one, geez. Let's just say one type. I was about to write one element. It's an element because it's only one element. Yeah, one type. Okay? Yeah, we run into issues all the time with this. Okay? If I was going to make water, what would I also need to mix in? Hydrogen. So we could write out our symbol for hydrogen. Hydrogen is also an equally special compound or special element. When we look at water or hydrogen, there has to be 2 of them as well. So I would write it as H2. Okay? What should I define that symbol as? Element, compound. okay, because of one type. If I make water, I take hydrogen and oxygen and I put them in the same space. Okay? Does that make water?
No, because doesn't it depend upon the mixture or the quantity?
Not quite.
No, because you have 2 oxygens.
We don't even have to worry about balancing it. What are you suggesting? Something has to happen to cause the hydrogen to be chemically linked to the oxygen. I can take hydrogen gas and oxygen gas and mix them. Believe it or not, it's already in our air. Hydrogen and oxygen are already floating around. That does not make water. What makes water is when I do a chemical reaction. In that chemical reaction, what have I done to hydrogen and oxygen? I have changed the chemical linkage. That means this big thing, hydrogen and oxygen over here, is what? If I take a look just in that big black circle here, this guy, right?
The compound.
Is it a compound?
No.
Are they chemically linked?
No.
No. So in that big black circle, I don't have a compound. Is it an element?
Yes. Well, no.
Says one type. How many elements are in this big circle? Damn it. So it must be then a pure substance. Are these chemically linked?
No.
Not a pure substance.
So it's a mixture.
It's a mixture.
You tricked us.
Yep, intentionally, sorry. These are now spatially linked elements. If I do a reaction, I can change that spatial linkage into a chemical linkage. What about what I see over here and over here allows me to differentiate that I've done that? So we could reference the reaction. Awesome, I love it. Try again. Because I would argue that you can still tell me this right here, H2O, is chemically linked, and these are not. Aren't these together? They're in the same circle. What do you got?
The format of how the compounds were,
What do you mean?
like the H2O together instead of separated. Like physically.
Does the empty space carry meaning?
Yes.
Yes. That empty space is showing that they are separate things. When I remove that empty space, they're now chemically linked. That could be hard to do or identify because it is altogether possible that if I was in a rush, I might have just said H2O, and I'm now saying, oh, those aren't chemically linked. Is that obvious? That space isn't as big as that space. How much space do I need to say they're different things? It has to be exactly 6 pixels. If it's 5 pixels, it's a compound. If it's 7 pixels, they're separate. That would be a pretty crappy thing to do to you, right? Okay. So what else could we add into that to help clarify our language to make sure that we know what's going on? That's all I gotta do? Yeah. Okay. Looking at the basic structure of how we organize the language of chemistry. A lot of this stuff was already kind of built in the back of your head. You just never acknowledged that that was there. It's there. Pay attention to it. Greg?
And that's what we call a writing system that is designed to encode information a specific way, usually within a particular environment. We'll talk more about that later. I just forgot to put it on the board.
All right. Kind of makes sense? So, to the note-taking thing, because I heard you talk about it, and I know it was an initial question over here. That's cool. Okay, remember, the course is overlapped. Right? So when we talk about chemistry content, we will be using the lens of the 8 aspects to try and apply to it. So what you might do is, because we're intentionally trying to bridge this gap, is that in your notes, you might have a special symbol or a special color. Oh crap, they just showed some cross communication about those different things. Because that's probably what we're going to ask about. We've intentionally built the course to do that so you can see those overlaps. You might really want to draw attention to that so that when you go back to study your notes, those could very easily be questions that we would ask later on in an exam. Does that make sense? Right? So for those of you with only one pen, you might bust out a different color. Get a highlighter or something like that. So that when we hit topics like this, you're like, oh, woo, they're going to ask a question on that. Okay? Some people may, it's not that big a deal. I would call attention to it, put it in your notes so that you know it's there. We're done at 45, right?
Yeah, don't pick up yet. We
Just
still
checking.
have 10 minutes.
I know that was all cool and phenomenal, and you're like, oh, he can't do any better than that. I still got the rest of the semester too, man. I sure hope that's not the pinnacle. Okay? So we good? Cool. Okay? So now we scaffold out and look at some of the organization behind the periodic table, which is going to get kind of an important aspect to be working towards pretty much starting this weekend. We classify the periodic table of elements into different sections. Metals, metalloids, and nonmetals. Right? Really, we have metals and nonmetals, and then we have this, what the hell is going on? That's metalloids. Right? And that's because when we look at it, our nonmetals are all found at the right-hand side of the periodic table. And our metals are all found at the left-hand side. Okay? Or towards the left-hand side. And if we went through, goad is the past tense of go, isn't it? We went through and looked at the physical properties of each of these things, we could start to draw conclusions about what we observe is happening with those. The observations of those phases becomes tricky because if I asked you to observe the density of silver, how would you observe it?
Touching it.
No, right now, literally, describe the density of silver. There's a little bit of a challenge there. What if I asked for the luster of silver?
Is that like the shiny?
Ooh. How'd you pick up shiny so fast, but you were stumbling over density? They're both observations of these.
Well, it's different between having it in person and having it in a picture.
Okay. So it's a differentiation between the picture and having it in person. A lot of the observations that we're putting on these lists to differentiate these are instrument-based. To determine the density, and we had someone mention it earlier, is mass and volume. Well, can I observe the mass of something? No, I can put the object on a balance and obtain the mass. I could use volumes and lengths and widths and stuff to calculate the volume. Okay? But I can't just look at it and say the volume is this, okay, with any real precision. So a lot of these kind of physical traits are very challenging to just know. Okay? Solids, that's pretty easy. Luster, how shiny is it? Okay? Our metals tend to be shiny. How malleable is it? Okay? Malleability is when I hit it, does it kind of squish or does it shatter? Metals tend to be malleable, meaning when I hit them, they squish. They don't actually break. Okay, so when I hit copper, what happens?
It goes to the shape.
Just whatever the impact was that hit on it. Okay, this is why we can make swords. Okay, with metal forges. Swords are made out of metal. If I tried to make a sword out of carbon, we run into a bit of a problem because what happens when I hit the carbon? It shatters. Okay, I wouldn't be able to shape it easily. Okay, so it has to do with the malleability. The conducting heat and electricity. Okay, conducts heat. I put a match on it. Does the heat pass through the material easily? If it does, that's probably a metal. That's a test. I have to do that. Or in the lecture, can you do a test? No. So how do you know pretty much malleable and down? Sort of accepting, trusting. How would you know for a test?
You'd have to have it in person.
You'd have to have it?
Like in person, you'd actually have to be able to do the experiment yourself.
Unfortunately, we can't do that either for a test.
Memorize.
You have to memorize it, right? So there is some stuff that you have to memorize. You're memorizing it because you trust us that we're telling you the truth, right? Which, for the most part, is true, right? Okay. So you would have to memorize that content. You might be able to say solids and shiny because you've had enough experience with those metals. You might not. Okay. When we move over to the non-metals, what do we notice? Well, they're mostly solids or gas. They're dull. Okay. What we're looking for is the differentiators. How do they differ from each other? Okay. They're almost opposites. That's why we might call one by a random name, and we might call the other one, since it's the opposite, a non whatever it is. Oh, lovely. Language is fantastic. We invented a word to describe one, and we said these other ones were not those by calling them non-metals. Okay?
I feel smart.
Oh, good. I'm glad I could do that. Okay?
Didn't say what you're doing.
Yeah.
What?
She didn't say what you're doing.
This is brutal.
Poor little feelings.
Let's take a look at all those pictures on another day, because I forgot entirely that we needed to talk about Project 1. Okay? I will say, as Greg's trying to get stuff set up here, that we've got metals and non-metals. The metalloids are branching in between. Okay? That in between happens to be this staircase. So everything to the left of that staircase is metals. Everything to the right of that staircase is non-metals. Some of that phase information is on the periodic table. Look at your key. Okay? The metalloids tend to fall on that staircase. Why do I say tend? It's not always. Okay? That's why I also don't ask about metalloids. Okay? Because they're a blend of pretty much everything. It makes it difficult to assign which element is a metalloid. Kind of make sense? Okay, go for it, Greg.
Okay, so I'm gonna take just 3 or 4 minutes to get you